Electric fields number 2, non-uniform fields, such as that produced by a Van de Graaff generator, produces a non-uniform electric field. This electric field is almost uniform, but you'll see that a sharp point, like a spire of a church, distorts the field a little bit. It becomes a little bit more concentrated at that point, which is why that point is most likely to be struck by lightning, because the field is strongest at that point. These are really the non-uniform fields you should know. The field produced by a uniformly charged sphere and the field produced by a point charge. There is such a thing as a point charge. For example, we usually think of an electron as having no dimensions, although it does have mass and it doesn't have infinite density, so it must have some dimensions, but we think of it as a point charge. Coulomb's law, similar to Newton's universal law of gravitation, Coulomb measured the forces between charges and he came up with a relationship that the force is proportional to Q1, Q2 over R squared. Now I've called the constant K, and that constant K is equal to very, very close to 9 times 10 to the 9, which is an approximation you'll be allowed to use in the exam. But the constant is actually 1 over 4 pi epsilon naught, where epsilon naught is a very important universal constant. It's called the permittivity of free space, and that's its value there. It's basically how well a vacuum allows an electric field to pass through it, the permittivity of free space, epsilon naught. So E equals F over Q. If we look at, well, combine that with Coulomb's law, we get E equals KQ over R squared, or E equals 1 over 4 pi epsilon naught Q over R squared. Here's a question that you can have a go at, have a read, stop the video, have a go at it, and the answer you should get is that. Potential in a non-uniform field. So we see the field lines on this diagram and we see the equipotentials getting further apart. The zero of potential here is taken as infinity, as it is with a gravitational field. Potential due to a positive charge is positive, because to move from infinity towards the charge you would have to do work. And so we imagine a potential hill. If a charge had to move closer to this big charged dome, you would have to do work. It would be like climbing a hill. And then if you were close to it and let go of the smaller charge, it would roll down the hill. It's a potential hill. Potential V equals KQ over R. That's the potential at a point due to a charge Q. Again, V is 1 over 4 pi epsilon naught Q over R. So the potential energy of a smaller charge next to this big charge would be QV, where little q is the charge of the smaller charge. The potential energy of a charge Q in the field would be QV, and the energy transferred if little q moves between 2 points within the field with different potentials would be QV. W equals QV. This is an interesting calculation which is relevant to the nuclear physics. It's to find what we call the distance of closest approach. An alpha particle with kinetic energy 7 megaelectron volts is heading straight towards a gold nucleus, which has a charge of 79 E. What energy transfer will take place as it approaches the nucleus, and how close will it get? So, pause the video, have a go, and there you go. The interesting thing about the value of R we get, it's not the radius of the nucleus, it's how close the alpha particle gets to it from the center of the nucleus. One thing it does tell us about the nucleus is that it must have a radius smaller than that. This is one of the ways that we know radii of nuclei are so small. Okay, now we mentioned earlier that field strength is potential gradient. In a non-uniform field, if we have a graph of V against R, then to get the field strength at any point on the graph, it's equal to the gradient at that point, the gradient of a tangent. So big E, field strength, equals dV dr. It's the slope of the potential hill is equal to the field strength. And if E equals dV dr, then V is the integral of E with respect to R. In other words, if I had a graph of E against R, then the area underneath it will tell me the potential at that point. So V is the integral of E dr. If you've studied gravitational fields, this should all be ringing bells now.